continue with another example. A mount steel beam has a solid section 4 cm square. So this beam itself, let's continue first. Alright, show the stress that distributes across a certain cross section. So the question tells us to show the stress distribution across this section, and if an applied moment M causes the plastic zone to extend over half of the cross section. So you want to show in a graphical diagram of it. Alright, so how should we start? Alright, we know that a mount steel beam has a solid section of 4 cm square. Alright, what does this mean is that I have a beam over here. Its cross section is 4 cm by 4 cm. Okay? You need to know that the mount steel, its yield strength is 250 megapascal. Okay? Therefore, if I were to look in this view right now, your particular beam, maybe I should change a different color. Particular beam over here, alright, has a certain, so this is 4 cm. Alright, this is 4 cm. And we have a neutral axis. If you still remember, this is a neutral axis. So therefore, this is 2 cm, this is 2 cm over here. Oh, this is 0. Okay? And it actually asks us to show that the stress distributes across the section that causes the plastic zone to extend. So you want to see some form of a plastic zone that extend over half of the cross section. So we somewhat need one. So if you were to talk about the cross section, right, somewhat going in this thing, somewhat like this. Alright, sorry, should be like this. Half of the cross section. Okay, so how do we draw this? So this one over here, alright, sorry, this thing over here is your beam, alright, and it has a certain distribution stress that crosses this thing over here, alright, half of it, alright. So the yield stress actually reaches half of this. So it's like the length, this total length is 4 cm. With the neutral axis, this becomes 2 cm, alright, and because it's a half stress plastic distribution as being described over here, causes the plastic zone to extend over half of the cross section, and therefore you're just talking about this point over here is plastic and the rest are still elastic, alright, so to speak, something like this. Alright, so this is the zone where you're talking about as a plastic zone. Alright, while your minus 250 and your 250 is just your yield stress, your milestone, your mount steel of your yield stress. Alright, because you're actually going downwards, therefore it's minus 250, and if you're this part over here is going upwards, because if you further bend, alright, your stuff is going to increase, right? You're going to have something like this, alright, and therefore your stresses is going to go in this manner. So it's 250 and minus 250. So far so good. Question actually asks you to, he didn't ask you to find your cross, your eye or your moment of area, but I don't know why the answer itself won't self-calculate for you. Alright, it says that for the given cross section of the beam, so I think he's trying to prove to you that this cross section is a full beam, right? It's not like a T shape or whatever. So therefore he's trying to prove to you that the cross section is this region. I don't know. And now it calls you to calculate M, your moment, and show that the stress distribution that have blah blah blah. Okay? So you just have to calculate the M first and see how it goes. Alright, so what do I mean by this? We're going to use this Holy equation right now. Alright? And we, instead of using this, alright, because now we're talking about this scenario where A is equals to C. Alright, so when A is equals to C, you can simply write as this thing, M is equals to 2/3 stress y BC squared. Alright, I actually didn't finish reading. When the material remain linear elastic. Alright, so we are just simply talking about this scenario. Alright, sorry, where's my pen? This scenario over here. Alright, so it's pretty elastic. Alright, so therefore we're going to use this formula. but because we know that we are actually concentrating on the magnitude, alright, so actually I didn't say in the past video, but you can rearrange this thing in terms of c squared minus 1/3 a squared, okay, as your U strength times the B equals to M. Alright, so we can simply rewrite this thing as this thing because we're only concerned of the magnitude itself. This is also reflected over here. Alright, this is 1/3 a squared minus c squared, and because we are just want the magnitude of M, therefore, which is more conveniently, we can express this 1/3 a squared minus c squared as c squared minus 1/3 over a squared, alright, which is exactly the same that we'll be doing. Let me show you. Alright, so this is the SYB. Alright, 1/3 a squared, I just simply change to c squared minus 1/3 a squared, which is same as this one. I just want to show you, at least you know where it comes from. We also say that for any elastic system like this, you can simply sub in your stuff over here. Alright, with this moment. Okay, so therefore let's take this. I'll just simply paste this equation and just bring all this over the side. Alright, just to show you that I'm using that equation. I didn't cheat your feeling. Alright, and therefore this thing over here is your SY times B times the same thing over here. Okay, now the yield strength of a material is 250 megapascal, and therefore it's 250 times 10 to the power of 6, where your B is the breadth, and we know that it tells us that we have a cross solid section of a 4 cm square. This means that the solid section of the beam, alright, this is 4 by 4 cm. Okay, and therefore it's 0.04 because 4 cm to meter simply divided by 1000. So 1, 2, 3, 0.0. Ta-da! What the hell is going on? 4 cm to meter is actually divided by 100, so it's 0.04, which is this one. Alright, and the c square. The c square is the stretch that you have been you have been stretched. Alright, in the elastic zone you actually stretch for 2 cm. Alright, over here this is 2 cm, and therefore we just sub it in as this thing over here. Alright, and you may wonder, firstly we say that this is C, this is A, this is 0, this is minus A, this is minus C, then why am I taking C, alright, as this thing? Why didn't I take this point? Alright, because we are talking about elastic region. So elastic region, instead of doing that stuff, we are starting from here, C to minus A, and therefore this whole C is in fact the length of 0.02, so to speak. Alright, I may be wrong over here, as my understanding may not be strong over here, but this is how I interpret. Alright, I may be wrong. Okay, so however this is just C square. Alright, minus 1/3. Alright, and then your A square, where's your A square? If such the case that happens, I believe that this is C, this is A, this is minus A, this is minus C. Ta-da! Alright, and then this whole thing over here should be 0.02. Alright, we are still safe. Alright, we are still using the understanding that we have done earlier. Alright, this is 0.02, this is C. Alright, where am I? Oh, okay, now I know what is C. This thing over here is C, because it's a magnitude of 2 over here, 2 cm. Then A is 1 over here. So yeah, this is just the understanding now. Now I get it. Okay, so this is A. Ta-da! And then you just work out, you have this moment, and then in the previous part, you know you calculated your beam, your I, your second moment of area, because if you remember the beam theory, mi over I. So you can just calculate what we have just now. Alright, and then the y max is the 0.02 over here. It's the distance from your top of your surface of your beam to the neutral axis, which is over here. This whole line is the neutral axis. Alright, and therefore this whole thing is actually 0.02, so to speak. Alright, and therefore you can see that this is your y max, while your m is this moment over here, while your I is calculated just now, and therefore you have your sigma max as your 344 MPa. For what you have is this thing that is talking about the pure elastic region. Right, talking about the pure elastic stuff. Okay, and that's quite surprising. But anyway, so at least you get something like this, the minus U strength, so the 344. Okay, and then you know that the moment is 3667 already. Alright, taking that you are saying that M had the material remain linear elastic. Alright, so you're talking about the linear elastic system. So you have this phenomenon that occur. Okay, so this is still elastic. And finally know what we are actually doing. Alright, if you take a look, if the beam is unloaded liao, alright, the elastic stresses in part B are recovered, because you know that the elastic system will go to its original state, right? For example, you have this thing over here. If it's elastic, you pull, it will become like this, right? But when you release, then you all the way go back to its original shape, something like that. Alright, so subtract these linear elastic stresses from your elastic stresses in part A, and then you shall see your residual stress. Therefore, we are actually calculating for residual stress. Alright, so we take this thing, minus away this thing, your plastic. So you have an elastic and a plastic regions over here, and then you find purely about the elastic. So you minus away the elastic part. What you're left with is all the plastic part. Alright, so just take a look. Alright, so therefore if you take a look, this is the part A of our stuff, is the plastic elastic. Alright, when your U strength is minus 250, you remember. And then part B, we calculated elastic region. Now we're gonna take this thing minus away your elastic region. So at this particular point is minus 344. At this particular point is minus 250. So minus 250 minus 344. What you have is minus 78 over here. Alright, so you have something like this. Okay? Sorry, my fault. Minus 250 minus 344. You're taking this point minus away this point, you have this point over here. I don't know what I'm doing, so it's 94. If you take your calculator, you just calculate, should be this. Alright, almost careless mistake, majiang. So now I take this point, which is minus 250 also, minus away 172. Alright, what do I have? I have minus 78, which is what we have said earlier. Okay? Then slowly at all these points, you just take note, it's all zeros, and the differences are reflected. So if 94 over here, you have a minus 94 over here. If it's minus 78, you have a 78 over here. Things like that. Alright. So therefore, your residual region is talking about all this stuff. So what you're left with is this region over here. Alright? And just to take note that your beam is still its shape like this, but within itself it may retain a certain hidden embedded stresses, and this embedded stresses, we call this the residual stresses. That if you were to input another force, in other words, if it's instead of this thing over here, you input a more stress over here, then you're gonna further increase this residual, such that you will actually break the system. Such of a case, I would say. This is a pretty much a good example for residual stresses. I shall see you in the next video for other stuffs.